Did was remove review and test for chapter 10. So rather than review and test last week, we're just starting in with 11 today. So we'll do 11:1 today, 11:2 Wednesday, Friday B again, A. So I got 2 days review built in, 2 days review. So one of them we'll do like the Frappy, one of them will go over your last test. At some point we'll, whatever we got to do to make sure we're prepared. So chapter 11 is only 2 sections also. So 10 was 2 sections, 11 was 2 sections. Most of our chapters have been 3 sections, so it's not a whole lot. And as you'll see today, there's not a whole lot of new stuff here. So here we go. Jump into it. 11.1. Test about population means. So we're going to be doing significance tests, except now it's going to be means. Now it's going to be means. So we're kind of combining all of our stuff from chapters, let's see, that'd be chapters 9 and a little bit of chapter 10, because chapter 9 was testing proportions, and then 10 was means. So what you know about means and what you know about testings is pretty much going to be combined right here. I jump right into the conditions for these because we know pretty much everything there is about hypothesis testing already. So I jump right into the conditions, and it's the exact same conditions that we've done for the last 3 chapters. We got to have randomness. We have to have randomness. We have to have 10% when you are not using all of them. When you're using all of them, you don't have to worry about 10%. So basically when it's an experiment. And then we got to do approximately normal. Means are different than proportions for approximately normal or large sample size, okay? So that one of those 3 things is going to happen. The population is normal, which that will not happen hardly ever. The sample is large enough. Remember, if the sample is larger than 30, then that follows the central limit theorem. If you guys can remember the central limit theorem, that's what that follows. And if that's not the case, they're going to give you the data and you have to graph the data. So one of those 3 is going to happen. So it's the exact same conditions as it is for means for confidence intervals. Exact same conditions. It's the same conditions for proportions, except the large counts and the approximately normal is different for proportions. Because for proportions, it's n times p, and n times 1 minus p have to be bigger than 10. And if it's hypothesis, or sorry, if it's confidence interval, it's n times p hat. If it's testing, it's n times p. So that changes all just a little bit. Those are the things you have to know the differences. That's where it starts to become a little bit difficult. But the number's 10, the number here is 30. So at some point, I'm going to give you a blank piece of paper and make sure that you know the conditions for whatever it is. And I'm going to just randomly pick one and say, give me the conditions. All of them are random, 10% provided that we're not an experiment, and then large counts. Most of them are the same. For means, it's greater than 30. For proportions, it's greater than 10. It's just making sure you know which one. All right, good with the conditions, right? We've done those several times. We don't use T procedures if that graph shows strong skewness or if it shows outliers. I have never seen one that does. I have never seen one that does. And again, I just typically use a box and whisker. That's just the easiest one to graph. That's the easiest one to graph. Beautiful. I don't know where all my students are. Oh, HOSA. All right. If you have to test it with the graph, guys, make sure you draw that graph on your paper, okay? So it's not enough just to make sure a graph, when assessing normality, you must sketch that graph on your paper. Make an appropriate comment about it. This graph shows no strong skewness. We have no reason to believe that this is not normally distributed or approximately normally distributed. Always use the word approximately in front of normal. So just make sure you make an appropriate comment. I like this graph does not show strong skewness or outliers. You don't have to draw more than one graph. A single graph will do. So just make sure you do that. You'll have to do that on my test. I'm going to give you the data, and you'll have to assess it normality by graphing the data. Just stick it in your calculator and do a box and whisker, transfer that over. Okay? Just transfer over. Prove to the grader that you actually did it. So we have hypotheses. Because we're testing significance test, we have hypotheses. So instead of P, it's going to be mu. Yep, hit me.
Do we have to graph it no matter what, or
only if it's less than 30? Only if it's less than 30. Right, only if it's less than 30. If it's greater than 30, you don't have to. Correct. Good question. So hypotheses, we have mu, right? And then mu is going to be whatever the claim is, right? 12 ounces in a Coke, it's 12. I don't know, GPA is 4.6, whatever it is. Okay, that's mu. And then the alternative is going to be mu greater than, mu less than, or mu not equals to. So we don't need to talk about what hypotheses are. Just the difference is making sure we're using mu, not X bar. Don't ever use samples. Don't ever use samples. Don't ever use samples. It's always the population. And these are not proportions. So if they're not proportions, we're not going to be using P. We're going to be using mu for means. So, not a big difference, but it is enough difference, right? You can see some multiple choice type questions. You'll see some P's, you'll see some X bars, you'll see some not equals to for hos, you'll see some equals to for the ha's, right? They're just going to mix them up however they want to. The hos always have to have an equals. The ha's have to have a not equals, I guess. You can have a equal to or less than or equal to or greater than on the ho. You can. Very seldom do you see it. So if this is greater than, this is kind of like less than or equal to. Or if this is less than, this is greater than or equal to. Okay? Just make sure you define mu. Tell me what mu is in the context of that question. Where mu is the true mean ounces of Coke, whatever it is, okay? Make sure you define it and make sure it refers to the population, not a sample. Students mess up a little bit more with mu's than they do proportions. They allude to samples every once in a while, not often. That's why it's true, the true mean. If you say that, you're alluding to all of them. I typically say the true mean of all. And then you're covering it twice. Okay, so just make sure we do that. Everybody okay there? Good, good. This is just a reference, a refresher, right? When it's greater than, it's an upper tail test, right? When it's greater than, it's an upper tail test. So we're worried about this area right there, right? We're worried about that right area when it's greater than. When it's less than, it's a lower tail test, right? Less than is a lower tail test. So we're just worried about the left tail, less than left-tailed. So we're doing a left tail test, or we're doing a less than. Sometimes they'll just ask for that. We're doing a left tail test. Well, then you know it has to be less than. If we're doing a right tail test, it has to be greater than. And then not equals to is a two-tailed test. So we're worried about both tails. Again, just things to think, oh yeah, I kind of remember that. Or I didn't understand it before and now I do. So we have one tail test and we have two tail tests. If it's greater than, it's a right-tailed. If it's less than, it's a left-tailed. If it's not equal to, it's a two-tailed. Remember that mu is always right there in the middle. That's what the claim is. That's what the claim is. We're going to get an X bar that's not mu. You're going to get an X bar that's not mu. So your question is, how far away is that X bar? If it's really far away, we're going to have to reject it. If it's not far enough away, then we're going to fail to reject it because we believe that that can happen. All that kind of makes sense when you see visuals of it. You're going to get some X bar somewhere. If it's two-tailed, it could be either way. If it's one-tailed, it can only be over here. I'm sorry, it can only be this way. It can't be over this way. So you're going to get an X bar somewhere around here or here. If it's here, you have to fail to reject it. If it's out here, you have to reject it because it can't be happening. So all that stuff still comes into play. Just like last chapter and all means, we are not using Z's. We are using T's. So just remember that. Anytime we're dealing with means, we are using T's. And again, it's because we don't know sigma. We're having to estimate two things, right? We're having to estimate the standard deviation and we're having to use X bar to estimate the mean. So because there's two estimations there, we need more wiggle room. And so T's we use instead of Z's. Remember what T's are, right? They have a little bit more area in the tails. They're a little bit shorter. They're a little bit wider. They're more area in the tails. As T's increase, well, T's don't increase, I guess. As DF increases, it becomes more like a Z. So we need to talk about DF. Here's the formula. I'll just do that first real quick. So the formula is the same, right? That's on your words. That's on your formula sheet. You got to turn that into variables. So your standardized test statistic is T. Your standardized test statistic for means is always T. Equals your statistic comes from your sample. Statistic comes from your sample. Your parameter comes from the population. That's what HO is. That doesn't look like a mu. And then your standard error of the statistic is the standard deviation of my sample over the square root of n. And all of that's on your formula sheet. Those are things that we need to know. And so our job is to find out what this T critical value is. We're going to turn that T critical value into a P value. We'll compare the P value to the alpha value. If it's greater, we'll fail to reject. If it's less, we'll reject. Yada, yada, yada. We do need to know the degrees of freedom. So here's all this stuff in non-hieroglyphics. The degrees of freedom is simply n minus 1. It's n minus 1. Okay? So one sample, it's always n minus 1. Two samples, it's that really nasty formula that you won't ever have to use. It's just what your calculator uses. Your calculator doesn't use anything here. You're going to have to tell it what it is. You have to tell it what the degrees of freedom is here for one sample. So it's just n minus 1. N minus 1. Anything I need to hit real quick while you guys are still writing? I mean, we've hit this formula several times. This part's on that formula sheet. It's on that next page, right over there on that right-hand side down a little bit. Degrees of freedom's not on your formula sheet, but it's just simply n minus 1. It's not Z distributions. So guys, you will not use normal CDF. Remember, we used normal CDF to turn this into the p-value, right? To turn that critical value, we use normal CDF. Well, we're not going to use normal CDF because it's not a normal. It's a T. So because it's not a normal CDF, we're going to use TCDF. TCDF. And that's under your distributions on your calculator. So you have a normal PDF, which you won't ever use. You have a normal CDF. You have an inverse normal. And then you have a TCDF. I don't even know if there's a TPDF. And somewhere there's an inverse T, right? We did an inverse T during confidence intervals. So we use TCDF. We'll do that in a second. I'll show you that on your calculator just to make sure. It will always go. I don't think it asks you the questions like normal CDF. I don't think. I'll have to look at it. I remember. But TCDF, it's always lower bound. And then you have to put a comma in there. That comma is just above the 7. So your comma. And then your upper bound, whatever. So this is negative 99999 to whatever the T critical value is. Or this is the T critical value to 99999. And then your degrees of freedom. Your degrees of freedom, whatever that is. Okay? Again, we'll do that for you in just a second on the calculator. But you need to know how to turn the T critical value into the P value. Remember what the definition of the p-value is, right? That's the proportion or the chances of getting the test statistic we got or the sample we got, assuming Ho is true. And then we got to put or greater or less. Remember that definition. That's important to know too. I don't think I talked about that in this chapter, but. All right, here's a quick question. Okay, quick question. I've given you everything. Let's just make sure we can kind of do this. Here's a lifetime battery of 15 deluxe AAA batteries from a company's random sample. So, simple random sample. Check if the conditions are met. Well, we have an SRS of 15 AAA batteries. Again, make sure you've tested it. And how do you know? Well, it tells me right there. Right there. I'm going to guess that 15 is less than 10% of all batteries. Look at there. That's nice. 15 is not bigger than 30. I don't know what the population looks like, so I got to graph that data. I got to graph it. So here we go. I have that data in my calculator already. What am I doing? Exit. What am I doing? Here we go. Here we go. Calculator. So stat, edit. Put your data in there. There's those 15, right? Remember now, I know there's 15 because when I go right here, it says L of 15. So that's L1 of 15 is 31. It's kind of like your XY. All right, so they're all in there. So I need to graph that. Y equals, I check to make sure I don't have any Y equals. I don't want any other graphs. So I get rid of all those. And I go up. So second Y equals turns your plots on. This one's already on. If you don't want it on, you turn it off. It's just a toggle back and forth. Oh yeah, I remember that. That's a scatter plot. Here's a time series plot. There's a histogram. And there's the box and whisker that we always use because that one shows outliers. You can use the other one. They're going to show the same thing, but I like this one because it shows the outliers. And we want to see if it has an outlier. I don't want L2 though, I want L1. So that's second one. There's where your L1 comes from. When I graph it, I'm not going to see anything because it's not there. So we zoom 9 it. Zoom 9. Beautiful. There's no outliers. There's no strong skewness. And so that's what I'm going to say. And I've got to transfer that to my paper. And then what I like to do, guys, I just hit trace. No, yeah, trace. Yeah, trace. That tells me that that's 33. So when I transfer that to my paper, I'll just put 33 right underneath it. And I'll go to the right and I'll put 44 underneath that. And I'll go to the right and I'll put 51. Right? It's just you don't have to draw each tick mark. Just put the numbers underneath it to prove to, that just shows you did it. Go to the left and put that number there. That's 27. And that number there is 17. And then you got those 5 numbers. That makes it look really, really, really good. It doesn't take that long to do all that stuff. Draw it like you see it, right? So off center that just a little bit, make that tail a little bit longer than that tail. But guys, you don't have to have a ruler out. This is not just prove that you did it. And that's why I like to put the numbers under there. If you put the numbers under there, just make that just a little bit longer and just off center that just a little bit, you'll be fine. You'll be fine. It doesn't have to be a graph, it has to be a sketch. There's a difference. So that's what we'll do. Let's go back here. Let's go keep. Let's go here. And then I'm going to say all that. So I'm here. Let's go red. And I'm going to draw a little bit longer. I'm going off memory. That probably should be a little bit longer, bigger there. Boom. And I'm going to put those numbers underneath it. I think this one was 33 and this one was 44. And I don't remember with others. Okay. no strong skewness or outliers. Beautiful. This distribution is approximately normal. Beautiful. I think you're lying if you say the large counts condition is met, because I don't really think that's large counts. That's why you had to graph it, because it didn't meet the large counts, because large counts says it's over 30. They'll kind of follow that, right? But they're kind of the same. So just get something in there and I think you're okay, right? These become harder. Let me rephrase that. These become more, how about less lenient on grading, and your work becomes more lenient on your grading. Now, because we got to understand what's going on. At the beginning, I'm less here, more on your work. But now we've done it a couple chapters. I'm less on your work and more on this. Good enough? Y'all okay? Because, guys, this gets its own EP or I right here, all by itself. That gets its own EP or I. Every time. Its own EP or I. So if you don't do it, that's the point you're missing. And some of you guys didn't do it on the test, so you're missing those points, right? Beautiful. SRS 15 deluxe. I didn't use the word deluxe. I don't think you have to. Assume 15 is less than 10% of all the company's deluxe AAA batteries. That's probably a little bit more than you have to write. Approximately normal large sample. The box plot does not show strong skewness or outliers. Beautiful. And there it is. Beautiful. Any questions about conditions? Suppose I want to perform a test. Ho, mu equals 5. Ha, mu does not equal 5. At the 0.01 significance level. A lot of times they'll give you what alpha is. Remember what alpha is? That's that borderline where we start failing to reject or rejecting. Right? That's also the chances of a type 1 error. Don't forget that. Right? Alpha is the chances of a type 1 error. A random sample of 37. Oh, that's nice. 37. N is greater than 30, so I'm approximately normal. From the population yields an X bar of 481 and a standard deviation of 0.365. That's typical. They typically give you those values. Assume that the conditions are met. Oh, that's nice. I don't even have to check the conditions. Explain why the sample gives me some evidence for the alternative. Well, the alternative is mu does not equal 5. The sample, X bar, is 481, which does not equal 5. That gives me some indication that this might be true. Or that the ha, might be true. It gives me some indication it might be true. I just got to see how far away it is. Explain why the sample result gives some evidence. That's some evidence. I don't know if it's convincing evidence yet. It gives me some evidence. The sample mean is 481. It's not 5. That's why it gives me some evidence. Calculate the standardized test statistic and p-value. So here we go. T equals X bar. I'm going to go ahead and just do this. You don't always have to do that, but it's nice. That way, if you do something wrong, they'll give you credit for it. They'll give you credit for it because you know what you're doing. You just don't know how to do it. It's okay. They don't care. 481 minus 5 over 0.365 over the square root of 37. Now, guys, I'll get a lot of students. Here's where a big uh-oh. I'll get some students put 36 right there. Y'all follow it. They put the DF underneath there. Careful. That's a lot of multiple choices, too. They'll put DFs right there. It's N. It's N. It's not DF. And so now we got to go to my calculator, and I got to punch all this stuff up, right? So let's do that really quickly. Show you 2 ways to do this. You need to know both ways. You need to know both ways. So here's my calculator. We'll quit and we'll get out of that. Okay, so one way is to just do this all, right? 4 point, was it 8.1? 8.1 minus 5, okay, divided by 0.36 divided by square root 37. So there's the t critical value. That's a pretty big one. Looks like it's going to have a pretty small p. So now we'll do that. Here we go. We're going to go second distributions. T, there is a TPDF. You don't ever use it. We'll use TCDF. Oh, nope, it does lower and upper. We're good. So we're going to go from negative 9999 because it's a negative t critical value. If it was a positive t critical value, I would put the positive t critical value here and I would do positive 99999. Upper value. Watch, I'm just going to hit answer because that's going to put the last answer there. So the negative 3 is going to be there. DF, 36. Paste it. Now that's going to turn it into the p-value. Oop! It's one tail test or two tail tests? There's the p-value because it was a two-tail test. Two-tail test. Because it's both sides. Yep. Because the ha was not equals to. If it's equal to, I'm done. Or no, if it's less than or greater than. If it's less than, it's the left-tailed. Because it's not equal to, it could have been this tail or this tail. I have to double it. If it's less than, it would just be that one. Doesn't matter. You're going to reject it both ways, but truth be told. I'd start after the 3. Y'all okay? See how I did all that stuff? I did the t critical value. Then I turned the t critical value into the p value, but I had to double it. I had to double it because it was a two-tail test. Let me show you real quickly also though, right? I could have just gone to this. Could have done stat, tests, and did a t-test. T-test is all it says. It's one sample, t-test. So we hit enter. I don't have the data. I have the stats. So HO was 5. X bar was 4.81. S sub X was 0.365. N was 37. And here's where I can tell it that it was two-tailed. And so this is going to do all of the work for me, which gives me that same t critical value and the p value. It does it both for me right there without having to do that. You need to know both. You need to know both because sometimes, guys, they're just going to give you the t critical value and they're going to say, are we going to reject or fail to reject? So you'll have to turn that into the p value by doing TCDF. But they gave me all the information. So if they give me all the information, I can do it all with one step. The calculator gives me everything. I don't have to find the t, then find it. That does the formula for me. It's embedded in the program somewhere. And then the p-value is embedded in the program times 2 because I told it not equals 2. So it already doubled that for me. So I don't have to worry about that. There's X bar, there's everything else. Anything about the calculator we might need help with. You'll have to practice on your homework for that. But you need to know both. You need to know both. This is easier, but sometimes they don't give you the X bar and the standard deviation. Sometimes they just give you the t critical value and then they say, what's the p value? So that's where you'll have to do TCDF. TCDF. What was alpha? 0.01? So we're going to have to reject. We're going to have to reject. The p is low, the HO must go. Right? P is low, HO must go. Calculate the standardized test statistics. So I did that. That was negative 3 point, anybody? 16? And the p-value, 0.003. Here's all this stuff. Okay, again, beautiful. This is telling you how, showing you how to do it on a calculator. There's the times 2. That's a good reason. Why do I need to multiply it times 2? Well, because it was a not equals 2. Because it was a not equals 2. Yep.
If it doesn't give you X bar or the
It has to. Has to. I mean, I don't know what to compare it to.
but then when you if it gives you T,
Oh, yeah.
so then if it doesn't give it to you, you just continue on with just using it.
Yeah.
You don't have to find it.
No, you can't. I mean, I wouldn't know what it was. Okay, just like all of our others, guys, it's a 4-step process. You got the method, you got the conditions, you got the calculations, and you got the conclusions. Okay, don't forget. The one thing students forget, the one thing is somewhere you got to put ho and ha. So I count that in the method. And so that's why when you did that, I'll see that. Okay. One sample mean t test. One sample, because there's only one sample. Means, because it's means. T, every time you write the word mean, you write T. If you write proportions, you write mean, Z. If it's means, it's T's. If it's proportions, it's Z's, always. Just the one thing, students, if they forget something, they might forget one of those, okay? That happened on last test. I just remember some kids forgetting to put what the ho and the ha are. The other mistake that a lot of students do, right? I've told you about this. They'll do that. Ho equals. You can't do that. You got to have the mu in there. You got to have that mu in there. Because we don't know if it's means or proportions. Now, we know it's means in this chapter because that's all we're doing. But on the AP test, it's all thrown in together. So make sure we say ho mu equals. Okay? So that's just one thing students forget to write. The second thing they forget, well, the biggest thing they forget to write is what DF is. That's always the biggest thing, writing what DF is. This is a fight between this and conditions of what they forget to put. But luckily, conditions has its own little deal. Conditions, and then the calculations, right? Now, guys, I'm telling you, this is less graded now than what it used to be. This is starting to get graded harder, and this is getting less. And so the way I tell you this is make sure you tell me name or formula. And if you do the method, then that's the name. You don't have to write the formula. But if you don't write the formula, you still got to tell me what X bar is. You have to tell me what mu is. You have to tell me what N is. You have to tell me what the standard deviation is. You have to tell me what T is. You have to tell me what the p-value is. You have to tell me what alpha is. Oh, and I didn't even put it. And you have to tell me what DF is. But most of those you got to list anyway. So if you tell me by name, you still have to label X bar. You still have to label what mu is, even though you kind of did that under the ho. But you got to tell me what X bar is. And that's why I like to write the formula. That's why I like write T equals X bar minus mu S of X square root of N, and then I don't have to label everything. I just go over here and write it. And that tells me what X bar is, and that tells me what mu is, and that tells me what everything is. But if you don't want to put that, it's okay. You just have to tell me what each one of them are. And a lot of people do that. If you notice that on my calculator, right? On my calculator, it did that. It told me what everything is, right? I just have to write all that stuff down. It's okay. T equals, p-value equals, X bar, standard deviation, N. Mu does not equal 5. That's the ha. Mu equals 5. So that's the stuff. You just got to put down what DF is. DF was 36. So you just have to label all that stuff. That's not what keeps people from getting E's and 5s. Really, it's not the work. It's not the work. And then it's not the conclusion. Most everybody does a good conclusion. Most everybody does well on the conclusion. Make your decision about ho, reject it or fail to reject it, and you either have enough evidence or you don't have enough evidence for ha, and then make sure it's in the context. Okay, all that's the same. Just make sure we use the word mean, don't use the word proportion. Right? The p-value is greater than alpha. We will fail to reject ho. There is not enough evidence to suggest, and then I'm going to go to whatever their question is. I went through that pretty quick. What question about something that you may or may not? Can I get credit if I do or if I don't? I'm just trying to make sure you get all your credit. I really believe you know what you're doing and you know how to do it. It's just you forget something is why you don't have full credit most times, more than anything else. It's just you forget to put something is why I have to mark off. The conditions is one. Ho and ha is a lot. Most everybody does well on the calculations now. Like I said, the calculations is not graded that difficult anymore. First couple chapters it was. Chapters 8, chapters 9, I graded this pretty hard. Now this becomes less, this becomes more. This becomes the big one, right? But each one of these gets its own EP or I. You got to have ho and ha, that gets its own EP or I. Ho, ha, define it. The conditions gets its own EP or I. The calculations gets its own EP or I. And the conclusion gets its own EP or I. You got to have 4 E's in order to get a 4. 4 points is a max. Well, then there's a multiplier. Each free response is graded 0 through 4 points. 0 through 4 points. And to get all 4 points, you got to have all 4 E's. 3 points, you got to have 3 E's and a P. And then 2 points is a bunch, different ways. Tell me what mu is. Mu is the true mean. Okay. I don't want to go through this real fast, but I'm going to go through it pretty fast. I'm not going to write down everything. Level of dissolved oxygen in a stream river is an important indicator of the water's ability to support aquatic life. Researchers measures the DO level at 15 randomly chosen locations along the stream. Here are the results in milligrams. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Again, that's not enough. I'm going to have to graph that. Okay. The average dissolved oxygen level is below 5. It puts it at risk. Does the data provide convincing evidence at the 0.5 significance level that aquatic life in the stream is at risk? That's provide convincing evidence. Guys, that's the full-blown process. We got to check conditions. We got to do the calculations. We got to state what ho is. We got to state what ha is. We have to define what mu is. And then we got to have our conclusion. This is a full-blown process, and it's going to take us 10, 15 minutes on the test, right? You got 13. So you got 13 minutes to try to get that done. Good enough? It's going to take you a couple minutes to punch everything in your calculator. So I got to punch all this in my calculator. Let me show you just a quick little speed up process. Maybe, I don't know. Get out of here. There you go. Because I did this already, right? Stat, edit. That's it, except what did I not put in? Decimals. So watch what I'm going to do. Go up. And I'm going to hit L2 divided by 100. A little bit quicker. A little bit quicker. Just kind of speed up that process. Now I'm not going to worry about this one. I could have done it right here. I could have done L2 divided by 100 here and just forgot about those. But now I'm looking at L3. So I need second y equals, and I need L3. Graph it. Not going to see it. Zoom 9. Oh, beautiful. Beautiful. So I got to put that on my paper. We have a random sample of 15 spots. think this one was a trick one because I don't think they checked the 10%. But I don't remember. I have to look. Beautiful. So we got 15 random spots, 10% if we did it. I mean, I guess 15 is less than 10% of infinity spots. And then that thing doesn't look skewed or have any outliers. So we're going to go with it. Right? The 3 conditions. Now, and I got ho. Let's go back to it. Ho, mu equals 5. Does this provide convincing evidence that the significance level that aquatic life is at risk? And it's at risk when it's below 5. So ha, mu is less than 5. Then you have to tell me what mu is. Mu is the milligrams per liter DO level. I don't know. DO level in this stream. In this stream, not at the 15 spots. How'd they say it? Mu equals 5. Mu is less than 5. Mu is the true mean dissolved in this stream. Conditions, random. Oh, it says there's an infinite number of possible locations, so it isn't necessary to check the 10% condition, but I think it's okay to check it. I don't think this one mattered if you checked it or not checked it. And then there's my graph, okay? And then, again, just don't forget to put this. And you don't have to put it at the beginning. You can put it wherever you want. I always put my conditions first just because. I'm starting to put this first now because I forget to put it sometimes. But that's why you draw that big old plus sign too, right? That big old plus sign helps you. Put the ho and ha in one of them, put the conditions in one of them, put my calculations in one of them, put my conclusions in one of them. The big plus sign helps you for these for sure. Okay? Notice that they didn't write the formula. They did write the formula, but they didn't tell me what X bar was, but they did tell me up here what X bar was. So it's okay. X bar is here. There's the standard deviation. There's 15. There's the DF. You don't have to write that. Okay? You don't have to write that. I'm just showing you in case that somebody's like looking through the notes. Like, how'd you go from here to the p-value? But again, I'm not going to do all that stuff. I'm going to let my calculator do everything. Let your calculator do everything. Okay? Stat, test, t-test. This is the t-test. You have to know what you're doing. Now I have the data. And it's coming from, there's ho. It's coming from L3. And we think it's less than, or we're trying to prove that it's less than. So it's going to do everything for me. And not only is it going to do everything for me, it's going to tell me what X bar is. It's going to tell me what the standard deviation is of that data. It tells me what the T critical value is, and there's the P value. Way bigger than alpha. Doesn't matter what alpha is. Doesn't matter what alpha is, we're greater than. There's N, it just doesn't tell me DF. You got to say DF is equal to 14. You got to say DF is equal to 14. But putting all this stuff is, that's going to be close to being good enough. That's close to good enough. You want to say the one sample mean t-test. That's the method. So you want to write that, or you want to write the formula, because that is one of the E's, P's, or I's. To get an E, student must name the procedure by name or formula. That's what it will say. By name or formula. You got to use that. These numbers doesn't tell me the name of it. One sample mean t-test. Put all that stuff, you're good. Correct. Yep. One sample mean t-test and put all this stuff. You don't have to put that, but put that, you're good. You're good. Anybody else have a question about that? I don't want you to not get credit for something, but just put all that stuff, put DF equals, and put it one mean t-test. One sample mean t-test, one mean t-test, all that's okay. And if you don't want to put that, put the formula. Probably easier to put the name. Just make sure you put one of the two, right? First couple chapters, what I do, I had you put both because I want you to, by now, hopefully you'll at least do one of them. By now, I hope you do one of them. And then we got to have our conclusion. Since p-value is greater than alpha. Now, make sure we listed alpha somewhere, right? If you didn't list it anywhere, make sure you tell me in the conclusion. But so I always put it right here. I put down this, DF, and alpha. I just listed all right there in my calculations. And then I don't have to write any more numbers. Since p-value is greater than alpha, we will fail to reject. Greater, fail to reject. There is not enough evidence to say that the DO level in this stream is at risk. Oh, I was there. Stat. It's kind of neat to see the actual draw. You can still see that box plot. But there's the T critical value. You can see the area is we're way too close to the mean. Because this is X bar. X bar is right, where'd it go? Why'd it go there? That's X bar. So we're way too close to the mean to be able to reject it. You have to fail to reject it. Because this p-value, that's the probability of getting this or less. Sometimes the graph helps you a little bit in that aspect of it. Beautiful. Because the p-value, 0.1816, is greater than alpha, we will fail to reject the null. We'll fail to reject ho, and you can say ho. But then you got to put in context. We don't have convincing evidence. Don't say we don't have convincing evidence for ha. That won't get you points. We don't have convincing evidence that the true mean DO, and again, guys, I'll go back here. We do not have convincing evidence that aquatic life in the stream is at risk. And I'll get it right from their question. Given your conclusion, what type of error could we made? Did we reject or fail to reject? Failed to reject, so we can only make a type 2. Explain this mistake, what it can mean. I think that it's okay for aquatic life to live here and it can't. We messed up. So type 2, we didn't find convincing evidence that our significance test, that would imply aquatic life in the stream is at risk. But we weren't able to detect that fact. Here's the link between two-sided tests and confidence intervals. I think we did a pretty good job on that the first time. If it's in the interval, you have to fail to reject. If it's out of the interval, you have to reject. I think we did a pretty good job on that the first time. So 95% confidence interval puts alpha at 0.05. It's whatever's left over. So you need to say at what level you reject it. You need to say what level you reject it. So if it's in the interval, I will fail to reject it at the 0.05 level. If it's out of the interval, I will reject it at the 0.05 level. You need to make sure we see the difference. So if it's 99, that's 0.01. If it's 90, that's 0.1. If it captures it, that's the pineapple one. I think we've done all that stuff. I don't want to. This was the year I didn't do a very good job on that, but I did it. I hope, guys, you can state the conditions. I hope that you can calculate the T critical value, turn it to the P value. I hope you can perform a significance test. And then I hope you can use a confidence interval to make a conclusion without having to do an entire test. 950. I think it posted.